Today we're going to do another launching experiment with another launching method. This time I'm going to use this launcher. So you simply place an object in front of this and then you push this button. Now this over here is exactly the same thing, but I'm going to show you how the mechanism works. So there's no spring inside of this thing. They're simply made of two things, this thing and then this button. You push this and then this pushes also. So this is like smeared with some kind of lubricant to make sure that it slides very smoothly. So the force that this pushes with depends on how hard I am pushing the button with my finger. Okay, so now to make sure that this one is always being pushed with the same amount of force, I've created this hammer setup. So this is a hammer over here. Okay, and over here is a piece of wood. I'm gonna pull this one upwards. Okay, so now I've raised it to a certain height, and the bottom of the hammer is going to fall on top of the button like this. Okay, in this way we can be pretty sure that it's always going to be the same amount of force that is going to land on this button. The bottom of the hammer, there's a little piece of cloth to dampen it a little bit. So, like this. The mass of the hammer is 469.1 grams. Alright, time for the results. So, the point of release was basically on the edge over here. So the ruler is right over here, parallel with the edge. Now the 2-mass ball landed mostly, let's see, well, in this area. I think around 60, 59 and a half. 59 and a half maybe, 60. This one is the 1-mass landed mostly on this line, which is around 83-ish, 83 centimeters. So we have 83 divided by 60, which is 1.38, or 183 divided by 59 and a half, we get around 1.39. So very close to the 1.4 number again, which is what kinetic energy predicts. Okay, results once again. So the 2-mass landed mostly between 47 and 48. And the one mass landed consistently on 66 centimeters. So 66 divided by 48 equals 1.37, and 66 divided by 47 equals 1.40. So roughly the ratio is between 1.40 and, well, between 1.37 and 1.40. And now let's try it out with these objects. So these are 2 discs, which is a 1 mass, and 4 discs, which is a 2 mass. Let's launch these objects. Okay, so the results. Once again, the 1 mass landed in this area, which is around, let's see, I think it's around 46 centimeters, 46-ish, and 1 mass in between here, around 65, 45, I mean 46, 65, 46, let's see, 65 divided by 46, that equals 1.41. That seems to be a perfect result. Okay, right, let's now increase the masses. I have taped two of these together. I'm gonna launch it, then I'm gonna take one of them and launch it and see what happens. Oh. Around here, right? Yep. Right, so the 2 mass landed mostly on the 29.5 mark. The 1 mass landed mostly around 49-ish. 49, 29.5. 49, 29.5. That equals 1.66. So this is a bit more. Yeah, 1.66 with these objects. Well, with the heavy, it seems to be the heavier the mass is, the bigger the difference becomes. So no, let's try out even bigger masses. And let's see if this is the case. Alright, so once again the results for the last time. The 2 mass landed roughly at what seems to be 18 centimeters. And then the 1 mass landed roughly what seems to be 29 centimeters. 29.18. 29 divided by 18 gives us 1.61. So once again, it's more. Instead of 1.41, it's 1.61. So with the heavy masses, we get a little bit bigger number. But it stagnates around 1.61, 1.65. When I increase the masses, it doesn't go higher than that. So the maximum number we get is between 1.61 and 1.66 was it, I think. Yeah, and the previous one it was about around 1.66. So that's like the highest number we could get. But for all the other examples, we had a 1.41. So yeah.